Today, I'd like to discuss the validation of highly accelerated real-time cardiac cine MRI with radial case-based sampling and then compressed sensing in patients at 1.5 Tesla and 3 Tesla. I'd like to start today's presentation with a quick overview of this paper. The goal of this research project is to validate radial real-time cardiac cine MRI with compressed sensing reconstruction in patients using 1.5 Tesla and then 3 Tesla scanners. There are a couple highlights in the methods they implemented in this study. The first is they use BSSFP radial sampling, and then they use 12-fold accelerated case-based data and then reconstructed the image using compressed sensing reconstruction. And then they compare these new techniques with traditional breath hold Cine sequence. And then finally, they evaluate the images with 5-point Likert scale and then cardiac function parameters. The 5-point Likert scale is a qualitative analysis, and then cardiac function parameters are quantitative analysis. I will elaborate the methods in the later slides. So in the results section, they state that there is no significant difference between new technique and the gold standard breath hold Cine sequence. But there are some interesting findings when I was looking at this paper and then doing related research. This real-time radial Cine has a relative short scan time, make it possible for claustrophobia patients to perform the scan, so they don't have to stay in the magnet board for a long time. And then this real-time Cine has a high temporal resolution, so it can benefit the patients with arrhythmia or tachycardia. And then this scan is also no breath holds. It can be applied to pediatric patients under general anesthesia. In this slide, I'd like to discuss the pulse sequence detail of this research paper. So they use balanced steady state through precision pulse sequence in the study. And then the balance in this case means that there is no night gradient dephasing in HTR. And then the signal intensity in BSSFP images is influenced by the tissue's T1, T2, and proton density properties. And then the signal intensity value for BSSFP is defined by the following equation shown in the top of the slides. And then in the bottom images shows the pulse sequence diagram of a radial sampling BSSFP. I got this figure from Dr. Andrew Larson's self-gating paper because the pulse sequence was not discussed in detail in the paper I selected. So there's one interesting part about radial sampling is that both the gradient X and then gradient Y are turned on at the same time during the Radial section, whereas in the traditional Cartesian sampling, only the X gradient is turned on during the readout. This phenomenon is demonstrated in the part A of the figure. And then in the part B, it shows the sampling pattern of a radial sampling. And then it shows a really important property of the radial sampling, which is the center of the case space got highly oversampled, and then the outer case space is not, the data point is not as dense as the center case space. Now I'd like to talk about the sampling strategy of this new technique. In the original paper, they call this section pulse sequence, but I think sampling strategy is a better description based on the information they provided. From the figure, we can see that each 2D slice frame takes a total of 3 heartbeats. In the first heartbeat, they perform a dummy scan. They use this section to achieve magnetization steady state. And then for the next 1.75 heartbeats, they perform a prospective scan, which is actual data collection. And then each radial spoke is spaced by tiny golden angle, which is 23.6 degrees. And then in the remaining 129.6 milliseconds, they perform a calibration scan where they collect 48 radial spokes Each of them is spaced 7.5 degrees from each other. This calibration scan is used to correct image artifacts from magnetic field gradient delays and the eddy currents. After K-space data is acquired, we need to perform reconstructions to get back to the image domain. The reconstruction method they use is called iGrasp. I got this figure from the original iGrasp paper. The first step of this reconstruction is to get the coinsensitivity estimations. They perform this estimate by first getting a temporal average and then combine the core images and then finally do the coinsensitivity estimation. After getting this coinsensitivity, they perform a resorting process to the continuously acquired golden angle radial data. So they are sorted in the order of time frame. And then those sorted image K-space data is fit into the iGrasp pipeline. The equation is shown in the above the figure. The F stands for the Fourier transform. S is the sensitivity map we estimated, and then D is the image to be reconstructed. The M is the data we acquired. The second part of the equation is the sparsity constraint. The lambda stands for the weights of the regularizations. It controls the balance between data consistency and then sparsity. And then T is the sparsifying transform. In this case, it's temporal total variation. After performing this iterative process, the image can be reconstructed from a K-space data. Now I'd like to talk about the qualitative data analysis. They invited 2 image raters evaluate the image quality of standard Cine and then Radial Cine based on myocardial edge definition, temporal fidelity, artifact, and then noise level using a 5-point Likert score, where level 1 is non-usable and then level 5 is excellent. Both Cines are got a similar score for myocardial edge definition. The standard Cine get a higher performance at the temporal fidelity in both 1.5 Tesla and 3 Tesla. And then the new Radial Cine got better performance in terms of artifact. And then for noise level, the Radial Cine is better at a 1.5 Tesla. And then at a 3 Tesla, both standard Cine and Radial Cine are performing similarly. In this section, I'd like to talk about quantitative data analysis. They use the stroke volume, left ventricle mass, and diastolic volume and systolic volume, and then left ventricle ejection fraction as quantitative analysis parameters. They compare the Radial Cine with the gold standard breath holding Cine. And then the plot shows the difference in each parameters compared with the average standard parameter. And then one interesting finding about this result section is that the end diastolic volume and systolic volume deviated a lot from the standard value in the real-time Radial Cine. Like what we discussed in the previous slides, there are a couple limitations to this new technique. The first is the inaccurate cardiac parameter measurements. They provided a couple of solutions to this problem. The first solution is to match a scanning parameter. In the results section, they mentioned that their scanning parameters is different in the Radial Cine acquisition and then the gold standard breath holding Cine. And then the second solution is to perform a breath hold real-time Cine. I think this method is harder to implementing because one of the key advantages of using real-time Radial Cine is to avoid the need for breath hold. And then adopting this approach could potentially negate the primary benefits of this innovative technique. And then the second limitation was this real-time Radial Cine. It's hard to select end systole and diastole frame. And then there are also 2 solutions to this issue. The first solution is to use image processing software to calibrate the time frame. And the second solution is to perform retrospective reconstruction of repeated real-time Cine scans. In conclusion, this study introduced an innovative technique for real-time cardiac cine imaging with promising clinical applications. The pulse sequence incorporates radial sampling, significantly enhancing acquisition speed and robustness against motion artifacts. The eye grasp reconstruction method, which integrates radial sampling, parallel imaging, and compressing techniques, effectively reduces image noise. While the new technique exhibits certain limitations, they can be addressed in the future research. Overall, this approach holds the potential to improve the patient's experience during the image acquisition and enhance the efficiency of cardiac MRI scans.